In this lesson, we're going to look at theorems that guarantee something. The first one I want to look at is this extreme value theorem. It starts off with an if statement. Here, if a function is continuous on a closed interval, all of those pieces are important. And if the function is continuous on a closed interval, then it guarantees that f has both an absolute max and an absolute minimum on the interval. So as long as blue is true, then orange has to be true. Let's take a look at the first diagram. In this case, f is continuous on the interval a to b. Check. So that should guarantee. So that tells us that the extreme value theorem applies. It tells us that we can guarantee that f has an absolute max and an absolute min. And we will just identify those. So the absolute maximum value of the function is 4. And the absolute minimum value of the function is not 2, but it looks like down here we'll call it 1. So the absolute max is 4, absolute min is 1. In the second diagram, I wrote f is continuous on the closed interval a to b. Unfortunately, this is just not true. At b, the function is not continuous. So this is not true. And the extreme value theorem does not apply. There is no guarantee that there'll be an absolute max or an absolute min. We can still look for them, but there's not a guarantee that there's going to be one for each. Let's take a look. In this case, the absolute minimum is still 1. Let's take a look at the absolute max. Well, there's an open circle here, so we can get to 3.5, 3.7, 3.9, 3.996, 3.9967. You see, I can keep getting a number that gets closer and closer and closer to 4, and so the limit would be 4, but it never quite equals 4. So there is no absolute max. None. Any number you give me, 3.996, I can give you a number that's bigger, but I can't say 3.99 repeating because that is 4. On the third diagram, I wrote f is continuous on AB closed. That's also not true. F is not continuous on AB. Consequently, the extreme value theorem does not apply. And so there is no guarantee of an absolute max and absolute min. Again, we can still look for them. There's just no guarantee in it. So this is just an exercise in finding them again. Absolute max is 4. The absolute minimum is 1. So let's state the theorem one last time. If the function is continuous on the closed interval, then it is guaranteed that f has an absolute max and an absolute min. And I often challenge students to give me a counterexample. Some function that you can draw that is continuous but does not have an absolute max and does not have an absolute min, or doesn't have one or the other. The most common challenge, and it's a very good challenge, let's call this a to b, and just for fun we'll call this the number 3, is students might suggest, hey, what if I drew a horizontal line, or a line segment in this case? Well, that certainly is continuous on AB, so the extreme value theorem does apply, and then there is a guarantee. So what is the biggest value of this function f of x? Well, the biggest value is 3. What's the smallest value? The same, 3. The extreme value theorem is sound. Let's take a look at the next theorem, the theorem that guarantees as well. This one's called the intermediate value theorem. In this case, if f is continuous on the closed interval AB, that's the same hypothesis. It's the same blue. So if a function is continuous on the closed interval AB, then the guarantee here is that f takes on every single value between f of a and f of b. and the same is true of the derivative. I'm going to erase this in a second, but I want to give you the sense that this is a no-duh theorem. So in this first diagram, the function goes from -1, f goes from -1 to 4. So all the values in between, let's say 0 and 2 and 3, they're all accounted for. Every number between -1 and 4 gets accounted for. It will take on, f will take on all of those values between -1 and 4. Now we'll do this formally. F is indeed continuous on AB. The intermediate value theorem applies. Here, f of A is equal to -1. F of B is equal to 4. Now, often the intermediate value theorem is used to guarantee the function has zeros. That is what I'm going to do here. I'm going to talk about the zeros of the function. There is a guarantee here that f of x will equal 0 at least one time. See here? F is taking on all values between -1 and 4, so it's going to include 0 at least one time. Diagram 2, f is continuous on AB. That is not true. F is not continuous on AB. The intermediate value theorem does not apply. Here, f of A is -1 and f of B is still 4, but there's no guarantee there's going to be a 0. And in fact, we see here that the function has no zeros. In the next two diagrams, f is continuous on AB, true, and the intermediate value theorem applies. And in both cases, f of A is equal to 3 and f of B is equal to 4. And in both cases, the guarantee is that the function will take on all values between 3 and 4. That's the only guarantee. We cannot guarantee that f will have a 0 at least one time. See, these diagrams were intentional that all of the pieces here were the same, but in the first one it did not have any zeros. But in the second diagram, which had the same qualities, it had several zeros. 1, 2, 3, 4, 5, 6 zeros to be exact. So the intermediate value theorem guaranteed that f took on all values between 3 and 4, but it could not guarantee, even though it's possible it had many, it couldn't guarantee it had at least one 0. The final theorem to discuss is the mean value theorem. This is the most mathy of the theorems, but it is another guarantee theorem. In this case, f is continuous on the closed interval a to b. That's been true of the last two as well, but this one adds, and also differentiable on the open interval ab, so smooth. It has to be continuous on closed ab and smooth or differentiable on the open interval. If that is true, then there's going to be at least one point inside AB such that, and I'm going to leave that a mystery for just one moment. Let's recall average rate of change versus instantaneous rate of change. The average rate of change of f of x on the interval AB, you should recall this from earlier in the year, the average rate of change as a formula is f of b minus f of a all over b minus a. Now how does that present itself graphically? Well, that's going to be the slope of the line connecting the endpoints. So the slope here is the average rate of change. Now, one of the fundamental ideas of calculus is that as this curve moves along, the instantaneous rate of change will change, and that's represented by the slope of the tangent line. So what's the guarantee here? If the function is continuous on the closed interval and smooth, then there has to be at least one x value between the a and the b here, such that, well, can you guess it? Well, such that the instantaneous rate of change equals the average rate of change. See, these two lines are parallel. The slope of this line is equal to the slope of the line in red. That's not the only place. I see here that the slope is also the same. So the guarantee is that somewhere between A and B, the instantaneous rate of change will equal the average rate of change. So there is at least one point C such that the instantaneous rate of change, f prime of C, equals the average rate of change. At least one time, because below we see in this particular diagram the instantaneous rate of change equal the average rate of change at C1 and another C2. So it can occur 5 million times, but the guarantee is that it occurs at least once. Here is example 1. F of x is equal to the square root of 4x minus x squared on the closed interval 0 to 4. F is indeed continuous on that closed interval. Check. F is differentiable on that open interval. Check again. Although you may be interested in the fact that this function is a semicircle here, and this is 0 and this is 4, and it's closed circle here, closed circle here, so the function is in fact continuous. You might note that at these endpoints we have vertical tangents, and because they're vertical tangents they're not differentiable, but luckily the theorem says it only has to be differentiable on the open interval. Yay! Now I'm going to find the average rate of change on 0 to 4. So that's f of 4 minus f of 0 all over 4 minus 0. And that comes out to be 0 minus 0 over 4, which is equal to 0. Now the instantaneous rate of change is represented by f prime of x. I'll find that derivative now. So that's 1/2 stuff to the negative 1/2 times the derivative of stuff. So that's 4 minus 2x. And I'll simplify that as the quantity 2 minus x over the square root of 4x minus x squared. Now, the guarantee is that the instantaneous rate of change will equal the average rate of change somewhere between 0 and 4, at least one time. You could probably guess it based on the diagram, but we're going to find this mathematically. So the guarantee is that 2 minus x over the square root of 4 minus x squared equals 0 somewhere. Well, let's see. We know that this fraction will equal 0 when the numerator equals 0. So we have to simply find where the numerator equals 0, as long as the denominator does not simultaneously equal 0, and it doesn't at x equals 2. So this is the value that satisfies the conclusion to the mean value theorem. It is the point at which the instantaneous rate of change will equal the average rate of change. And I will ask that you humor me by telling me that this is an element of the open interval 0 to 4. That is a reminder that you only want the ones that are inside the interval, not including the endpoints, not including anything outside the interval, but you write this to show me that you know what you're looking for. Perhaps you come up with 4 answers. You only want to identify the ones that are in the correct interval. In example 2, we take a look and we can say here that G is continuous on the interval 0 to 3. That is true. However, G is not differentiable on the open interval 0 to 3. You certainly should know what this looks like. This is a V shape shifted over 1, so it's going to look like this. 0, 1, 2, 3. You see that this function is not smooth or differentiable at x equals 1 because we have, if you recall, what's called a corner. A sharp transition is not smooth, it's not differentiable. Here, the mean value theorem does not apply. You could go on to find average rate of change of g and the instantaneous rate of change of g, which, mind you, would be a piecewise function, because this can be written as a piecewise function. But whatever. You could find the average rate of change and the instantaneous rate of change, and I guess it's possible there'll be times when those are equal, but in this case there is no guarantee, and we're not going to find them because they do not exist.